Hello, today we start the second half of our exponentials chapter talking about their inverses, logarithms. Today is just an introduction to logarithms based on the fact that they are inverses of exponentials. So from our in-class work, we need to remember that we can transform exponential functions in the form b to the x equals a to logarithmic functions, where b is still the base of the logarithm. The exponent becomes the output, and the output of the exponential becomes the input of the logarithm. Logarithms, when we talk about them, we say log base whatever number it is, and then the inside, the input, is called the argument. If your argument has more than one term, you need to use parentheses. Your argument can never be equal to 0 or negative. So we need to make sure that every time we write a logarithm, we understand that. We know that logarithms and exponentials are inverses of each other, so we are going to do some work and find the inverses algebraically. Like we were doing in our last lesson, to find the inverses algebraically, we switch the x and y variables. The difference here is once we have isolated enough, we convert from exponential to logarithmic form or vice versa. And then we solve for y. So we're going to get to a point where we're like stuck with the math we know, and that's our cue to convert forms. How do we convert forms? Using this. So example 1, switch x and y. Isolate the exponential. So we add 3 to both sides. X plus 3 is equal to 2 times 5 to the y. Divide by 2 on both sides is equal to 5y. At this point, I'm not really sure how to solve for y. It's stuck up in the exponent. That tells me to convert. So because I'm an exponential, I'm converting to logarithms. So I write log. The base is going to be same as the base as the exponent, so 5. The output of the exponent becomes the argument of the log. So this is the output of the exponent. X plus 3 over 2, that whole entire complicated thing becomes the argument of the log, equals to the input of the exponent, y. In this case, I'm done solving. We have y isolated. Sometimes I'm not done solving and I have to go further. The last step we always want to do is recognize that we just found an inverse by replacing our y notation with f inverse notation for our final answer. Example 2 has a special type of logarithm. There are 2 special types of logarithms that we talk about, and the first one is here. ln is really log base e, but it's so common and mathematicians are lazy. They hate writing out 4 letters when they can just use 2. So they came up with ln. It stands for natural log, and it's a log that shows up in math quite often. So we need to recognize it as log base e when we see it. We start by switching x and y, and we work towards isolating the log in this case. Now, there's not any algebraic work for me to isolate my log in this problem. So I start to look for any algebra I might be able to do. The log and the argument can't be split up through any multiplication, division, addition, subtraction like that. That tells me that I need to convert. Because I'm in logarithmic form with the log isolated, I need to convert to exponential form. So the base of the logarithm is the base of the exponent. The output of the logarithm is the input of the exponent. and the input of the logarithm is the output of the exponential. Here, y is not isolated. We need to remember to solve for y. The way to solve for y in this case is by taking the square root of both sides. We are solving for a variable by taking a square root, so we need to remember the plus or minus. So we get y is equal to plus or minus the square root of e to the x. Recognize that you found an inverse using F inverse notation to get your final answer. Next, we'll talk about graphing logarithms. We're going to use the fact that exponentials are the inverse of our logarithms. So from our exponential in the graphing lesson, we know the parent equation is this, the table looks like this, and we have an asymptote at y equals 0, domain and range. Therefore, for the logarithm, we can use the fact that it's the inverse to fill out this information. I gave you the equation for the parent. It's a really basic form with just the base and x in the argument. Anything else is a transformation. So to get the table, we're going to use the exponential table here. And remember, the input becomes the output and the output becomes the input. So here, our input was 0, 1. Our output was 1b. So this is now the parent table of our logarithm that we are going to use to graph. Another property about inverses is that the domain and range switch. So if my domain is negative infinity to infinity for exponentials, my range is going to be negative infinity to infinity. My range was 0 to infinity for exponentials, so my domain is 0 to infinity for logarithms. The other thing that switches, instead of having a horizontal asymptote, we are reflecting over the line y equals x to get this graph of a log. So we have an x equals or a vertical asymptote at 0 for the parent. We're going to treat that the same way we did with our exponentials, and we're going to carry it along with our parent table, and anytime we change the x's, we'll change our asymptote. So if we think about a parent exponential, and we'll do exponential growth, something like this. It's an elbow shape with an asymptote right at y equals 0. If we reflect that over the line y equals x, which is this line here, I'm going to draw it in blue, reflect it over this. So we're folding our imaginary piece of paper right on this dotted blue line. Our horizontal asymptote becomes a vertical asymptote right here. The point 0, 1 becomes the point 1, 0. The point 1, 4 becomes the point 4, 1. And we're looking at an elbow shape kind of like this. It has the same properties that our exponential parent did, where we never touch that asymptote, but we get super, super, super close. So we will look through one graph, and then you guys will be working on some practice as homework. We begin with our parent. Our parent function is going to be y equals log of x. Now we notice here that there is no base written, and that is because this is the second type of special logarithm. It's called the common log. So the common log has base 10, but we don't write it because it's common. So anytime you see log without a base, you have to assume base 10. So this is our parent, giving us the parent table 0, 1, 1 base, and the asymptote x equals 0. The transformations that happen in the parentheses of the logarithm are your horizontal changes, and then everything on the outside is your vertical changes. So our first transformation we see is subtracting 3 on the inside, which means write 3, which means add 3 to all of your x's. So 4, 13, even your asymptote. So 0 plus 3 is 3. Now our asymptote is at x equals 3. The next change is a 2 multiplied by x on the inside. We have to remember reciprocal. So this is actually a horizontal shrink by 1/2, which says multiply all your x's by 1/2. So we have 2, we have 13 over 2, and we have x equals 3 over 2. Our y's stay the same. The last transformation is adding 4 on the outside, which means up 4. I'm going to work down here, which means add 4 to all of my y's. So 2, 4, 13 over 2, 5. My asymptote will not change. X equals 3 over 2. I always graph my asymptote first. So x equals 3 over 2 is a vertical line right at 1.5. And go plot that. Now I had no reflection, so I'm expecting it to look like this parent logarithm just shifted around the graph and stretched or shrunk. I plot the points 2, 4, and 13 over 2, that's 6.5, 5. And I make my elbow shape that approaches this asymptote to the best of your ability. The elbow shapes can be hard sometimes. The last step is your domain and range. The domain is cut off by the asymptote. So our domain is going to be from the asymptote, but not touching it, to infinity, because we're going off to the right. And then the range of any logarithm is negative infinity to infinity.